capacitors actually have a very interesting property. If I connect a couple up in series, give them a 10 volt supply, as long as these two capacitors have the same value, so say 22 microfarads, then the voltage you'll see across each capacitor is half the input voltage. So that'll be 5 volts. We'll have 5 volts here as well. So of course the output voltage is equal to the input voltage, but the capacitors divide the voltage, which is kind of cool. And they divide the voltage in relation to the capacitance. So this was 2.2 and this was 22. That would see 9 volts, that would see 1 volt. However, keeping them both the same, we get a voltage division happening. Now that's really interesting because it introduces the idea that we can use capacitors to step down a voltage. If we can charge them in series and discharge them in parallel, then we can use this to convert 10 volts down to a 5 volt output. Now of course it's pretty easy to do that. All we have to do is take those two capacitors and connect them up in a switched network. So it looks like this. Of course, mechanical switches are a bit of pain in the neck and we don't need to use them. We can put some diodes in, and if we bang the diodes in into a little network like this, then we will achieve that effect. We'll have that effect where the input voltage is divided by 2, as long as the capacitors have the same value. Of course, that is pretty awesome, because it gives you the possibility of creating transformers without using great big solid lumps of iron, without using copper, and without using magnets, and that's got to be interesting, hasn't it? There is one big drawback, incidentally, and the big drawback is they're not very efficient, which is a real shame. Now, have you ever thought that we actually live on a great big capacitor? Here on the ground, of course, we've got one capacitive plate, and up there we've got the ionosphere, and between we've got a whole load of air. So the Earth is a massive capacitor. Capacitors are extremely interesting, and a lot of people have been given a lot of thought to this problem. The problem really lies in the diodes. There's a big voltage drop across those diodes. They used to use MOSFET switching, gave up on that because that was even worse, but there's still a big voltage drop until a group of scientists had to think about this and came up with the idea of using fractals. So, what is a fractal? So to use that fractal idea, let's take our two capacitor network, zoom down on each capacitor and replace each capacitor by another two capacitor network, and then we get this. And if we take that and zoom down on each capacitor and replace each capacitor by a two capacitor network, we get this. And so the fractal design grows. Now, if we take our basic fractal capacitor design with 4 capacitors in it, then it looks like this, and if we want to charge it, then we flip the switch here, and the charge route is following the red line to charge it up. To discharge it, we flip the switch right the way on the other side, and now the discharge is following the red route to discharge it. So with that little arrangement, we can charge any number of capacitors up in series and discharge them in parallel, which if you think about is pretty awesome, because of course capacitors come in values that will handle kilovolts. So we could bang kilovolts in one end and get tens of volts out at the other end. Now the report is that this is about 94% efficient, which is incredible when you think about it. And the other really interesting thing, of course, is we don't need to buy capacitors like that. Capacitors are dead easy to make. You just a couple of metal plates either side of a bit of plastic, you've got yourself some capacitors. So using that, we can put together a capacitive network that we could print that will take kilovolts in one end, tens of volts out the other end, or even a volt or two. I made a diode. It's an AD Moore electrostatic device, and I made an electrostatic diode that generated high voltage and low current, like all electrostatic machines do. Now, it really, to my mind, is a way forward for generation, and if you think about it, it's mass-producible, it's cheap, it's lightweight, it uses no magnets, no steel, no copper. It's just awesome if we can resolve one tiny issue. That tiny issue is the conversion of that high voltage, and we're talking sort of 5 to 10 kilovolts, and the nano to micro ampage that such machines to produce into the reverse, that is, high ampage and low voltage. Now, that's a challenging thing to do when you're talking about such voltages, until a friend of mine, Tiago actually, pointed this out to me. So here is what started it all, and again you can see the address here at the top bar if you want to get to this, and it's the flexible circuit wind generator. Now, it's an electrostatic device, and it's well worth having a look at this. But if you have a look at the circuit for the wind generator, you should be reminded, or at least I was reminded very strongly, of the electronic Bennett's doubler that we just saw. So this idea here of using those capacitors to convert high voltage, low current to low voltage, high current has got me very excited indeed, because that concept is based on something called switch capacitor conversion. We want to know about switch capacitor conversion, in particular fractal switch capacitor conversion. This paper is absolutely awesome, and if we go through there, then we'll get a good idea of what this actually is and how this works. I want to point this out to you. This is a standard AC transformer, and here we can see the basic switch capacitor converter where we're switching capacitors between parallel and series. So we connect them in series to charge them at high voltage and low current, and then reconnect them in parallel to discharge them at low voltage but high current. Now, that has lots of losses involved, but according to this research paper, what they're calling this fractal design here mitigates against those losses. Suddenly, everything becomes exciting. So that's a flexible linear aerostatic generator, spelling FLAG, which I think they chose that name because they're a bunch of very patriotic Canadians, so it's kind of cool. But it used something called a fractal series capacitor converter, and that concept astounded me. Never known that concept before. Thank you very much, Tiago, because that little route led me through to there. Now, I've been interested in electrostatic machines for a very long time, and it's mostly actually courtesy of this chap. And I want to quickly show you his website, because his website is just a mine of information. So this is the guy that I'm on about, and you can see the address here, www.coe.ufrj.br. And personally, I think the guy's a genius. Whenever you want to, whenever I want to find some information about an electrostatic machine, this is the guy that I tend to go to. If we scroll down there, you'll see some absolutely fascinating builds of all kinds of machines that this chap has built. But the ones that I really want to pull your attention to are these electronic versions. He's bothered to do, well, I say bothered to do, the guy actually does an awful lot of research in this, and he's made a lot of electronic versions of electrostatic machines capable of harvesting energy. This one is the one that really started me off, was the electronic version of the Bennett's doubler. The Bennett's doubler is an exceedingly simple induction machine, and you can see what he built here, and then a series of 1N4007 diodes going up to 5 kilovolts to harness the microamps that could be gained just by moving this disc between those two discs as a variable capacitor. He also built something on the same version using what's called a Wilson machine. And if we scroll down to get a better view of that, you can see that the Wilson machine is basically a couple of variable capacitors set to rotate that he then harvests the energy from using a set of capacitors and diodes. Absolutely genius. And looking at that, you can see a kind of line from the electrostatic machines of Moore, the Bennett doubler, the Wilson machine, the FLAG machine we've just looked at, and this FSCC converter we're now looking at. All of that stuff, I think, is coming together to give us the ability to print an electrostatic machine and print a great part of the converter, because those capacitors that were used for that series parallel step-up, step-down configuration could be equally printed in the same way that the actual electrostatic machine can be printed. That's got me super excited, because we're looking at something where we can actually be able to produce something again no wires, no metal, no magnets, printed on a bit of paper, probably, but certainly plastic, that can be used to generate, and that tricky task, convert from high voltage to low voltage high current. That is what I'm going to be working on, and it's mostly Tiago who's to blame for that, because that is something that's been a bit of a holy grail for me, and I've had the pieces in place, but this final bit, which is actually pulled from this paper. So we're going to be drawing and making this fractal capacitor. So first of all, we need to draw the circuit, and then we can build the capacitor. Now, fractals, as you look at them from the broad scope, look intensely complicated. But when you zoom in, there's actually very simple few rules that govern the growth of a fractal. So, for instance, here's a really simple fractal. Let's say we take a line. And then the rule is, at the midpoint of every line, draw another line that is a third the size of the initial line. So we take a third of that line, go halfway, and draw a line at 90 degrees. So we do that. And that's the rule. But we have to repeat that time and time again. So we do that. And we keep on doing that on every line that we see. And as you do that, you get a very complicated shape. In fact, that's the arm of a snowflake. It's how snowflakes grow. So we can continue with that, taking a simple rule, applying it, and we create a complex image. Another example of this would be a triangle. So draw a triangle. And the rule is, every third, another triangle, a third the size. And then obviously we repeat that again. And again. And we keep repeating that, going round and round and round, and we create a fractal. Okay, so to construct this as a fractal network, let's start with the original circuit, which is this. Now, I think that's a little difficult to follow. So if we remove the capacitors and stretch out the diode string, what we get is this. And that's the diode string just stretched out instead of that Z formation. And if we put the capacitors back in place, then we get that. Now, I think that's much easier to follow what it is we're going to do than this one, which confuses it a bit. And with this one, then we can see quite clearly, what we have here are 3 diodes in a string with 4 connection points. Now, the bottom is the negative, the top is the positive, and you can see where the capacitors are connected at those connection points. So all I've done is put these dots on here so that we can follow this. These dots represent the joining points, and we've got 1, 2, 3, 4 with 3 diodes. 1, 2, 3. The things to notice is that 1 goes to the capacitor, 2 goes to the capacitor, and remember 1 is the negative, then 3 goes to the other side, and 4 goes to the other side of the capacitor. So capacitor here is joined at dots 1 and 3, and this one here is joined at dots 2 and 4. And as long as you remember those, constructing it is really simple. So first thing, let's get rid of the capacitors. And now we need to introduce another string of diodes. The diode string is going to get connected in the same way that the capacitors were. 1, 2, 3, and 4. Now we would connect up the capacitors, and they connect them the same places. And we've done the first iteration. Now for the second iteration, let's get rid of the capacitors. Our next string of diodes. And our next string of diodes follow the same pattern. Now we've connected that next string of diodes following the same rule that we did before. 1 and 2, and 1 and 3, 2 and 4. And so the diodes are connected in the same way as the first iteration and the second iteration, and then this iteration. And now what we want to do is connect up the capacitors, because we're at the bottom of that iteration. The capacitors connect up here. Now we have our next iteration, and we could continue doing that. There we connected the capacitors, but if we put another string of diodes in, we would obviously get 18 capacitors. Sorry, 16 capacitors, not 18. 18 is 16. Now, because we're repeating that rule set and we're connecting everything in the same place, and as we drill down on it, we can continue to repeat that rule set, then we're constructing a fractal. Because the fractal is being constructed out of capacitors at the end of the day, it's a capacitive fractal network. Now, somebody has asked, can this be done the other way? Because what we're doing, obviously, is stepping down an exceedingly high voltage. Can you step the voltage up? And the answer is yes, you can. When you charge in serial and discharge in parallel, we're going to have a step down. When we charge in parallel and discharge in series, we're going to have a step up. So reversing it is pretty easy. We're interested in the electrostatics, so we're looking at step down, but yes, you can do a step up version of this as well. And you can drill down into that fractal network as much as you please, and obviously you can connect two fractal networks together. Remember, in that diode string of 3, the bottom was the negative, the top was the positive, and it's the main center diode string which is the positive and negative. If we connected them to another main center diode string, we would have two fractal networks joined together. So we can either drill down on the fractal network to create a deeper and deeper fractal network, or we can join two fractal networks together. We need to make chains of 3 diodes. Let me give you a close-up of the process. Okay, I think it helps if you think about it like this. We have a string of 3 diodes, and to that we connect 2 capacitors. And those 2 capacitors connect at points 1 and 3 and 2 and 4. Now it becomes fractal when we remove the capacitors, which are the connections here, put in another string of 3 diodes and connect 2 capacitors. Then we can remove the diodes again, connect. So each one of these lines represents a string of 3 diodes. The termination here represents the capacitor. It becomes fractal because we can keep on doing that, getting smaller and smaller and creating a fractal pattern. And we can continue down doing that, creating that pattern, going down and down and down, making a fractal. And that's why it's a fractal capacitor. Now I think this image helps visualize what it is we're actually doing. So remember, I have a lot of diodes, and I bought 1,000 diodes for £7, so they're really, really cheap. And you take 3 of them, and obviously you've got a little silver band and a black bit, and all the silver bands point in the same direction. So you need to make sure they're all pointing in the same direction. Then you twist them together like this and solder them there, so we've got those 2 wires. Now what we have are 4 connection points. Here, 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 and here. For the sake of argument, let's call that 1, 2, 3, 4. To make this, we're going to use 4 wires, and we're going to connect those wires up to the capacitors. So in order to put 64 capacitors on our fractal net, what we need are 32 of these, because each one of these takes 2 capacitors. We solder the same wire in the same place all of the time, so we know what we're doing. And here's an example of one that I've got ready. And you can see that what I'm calling position 1 is black, position 2 is blue, position 3 is red, and position 4 is yellow. And I need to solder them all the same way every time. So the black will go there, the blue there, the red there, the yellow there. And as long as I make 32 identical to that, then at this end, once I've made those, then I can solder the black and the red to one capacitor and the blue and the yellow to the other capacitor when I form my fractal net. Now, we obviously need to build these out, so what we're going to do is solder up another one, and I'll show you then how those two join up. Okay, so once we've made 2 of those, you can see that I've done them on the same sides. There we go. Black to the bottom, yellow to the top, and they're all the same. We need to join those up to another string of diodes, and here they are. And those diodes are done in the same way as the first string, black to the bottom, and we solder these on 1 and 3, just like we did with the first capacitor. Then this gets soldered on 2 and 4, so that we get that arrangement. Because it'd be annoying to have them that way, because we've got to stack them up even more, so we need to do it that way around. And we do it that way around. Here's the first one soldered on. The second one would get soldered on 3 and 4, and it would end up looking like that. And we do that because we're going to do another set. And on that other set, we're going to have another string of 3 diodes. Again, black to the bottom, and they get soldered on 1 and 3 and 2 and 4. And we keep doing that, doubling them up. There's a slight issue. These wires are bare, so we need to stuff something in there, like a bit of tape or plastic, to stop them hitting each other. Now let's solder them up again. Now just put some strips of plastic in there just to separate those wires out, and we do exactly the same thing. There's our strip of 3. We soldered this black wire to junction 1, if you like, this top wire to junction 3, and then the next one gets junction 2 and junction 4, and we get that. And again, I'll put a strip of plastic in there to keep the wires separate, and we'll build up for the next layer. Okay, we continue up, pairing them in the same way across a string of 3 diodes until we get to the last string. Now in the last string, you'll notice there's the band there, there and there, pointing to the red, and the black is pointing to the bottom, and this is your negative connection and positive connection for the in and out. And now all we have to do is connect the last 2 bundles in the same way. So bundle 1 goes junction 1 and 3, bundle 2 goes junction 2 and 4. So what we end up with is this. Now, granted, it is perhaps not the most elegant way of doing it, but I think it helps visualize what we've actually done. We've taken that fractal pattern, we've taken the string of 3 diodes, and we've built it down and down and down to physically create something like this. Now, as I pointed out, that's your positive in and out, that's your negative in and out, and each one of these represents a pair of capacitors. So if you remember, the red and the black go to one capacitor, and the blue and the yellow go to the other capacitor. Each one of those needs a capacitor on the end of it. Now, you can use an ordinary capacitor, but I of course want to make the capacitors so that I can then paint the capacitors. And so that is what you end up with, but you end up with it through that process. Now, as I said, this is just to help visualize. If anybody points out to me it would be better to do this on a circuit board, it would be 100% better to do it on a PCB. But I do think you would miss how it's actually built if we just went straight to the PCB. So that's how it's actually built. And we made this bundle of wires and diodes to explore how it was actually made and what the theory was and why it was been built that way. But I appreciate that doing something like that is really just a teaching exercise as opposed to something you would actually want to do in real life. So I've taken the trouble of drawing up the circuit, and here it is. Now, of course, that's useful in itself. You can just pause the video and copy the circuit if you wish. But I went one step further and downloaded EasyEDA and turned that circuit into a PCB, which is here. Now that PCB is quite large. It's actually just a little bit smaller than an A4. Costs, I think it's about $4 to actually have each board made up. And there are a lot of components on it. But that is a 96 capacitor fractal capacitor. That's the circuit diagram for it and the PCB arranged in Java files for you should you actually want to do that. Now I appreciate that that's a lot of information and it might seem overly complex, but to my mind it's the key for unlocking atmospheric energy. It's a key for unlocking the power in lightning. It'll take an extraordinarily high voltage that we couldn't otherwise manage and turn it into a voltage that we can manage and acts just like a transformer. So the voltage drops down into your boots, but the amps goes up into the sky, which is exactly what we want to do, and it's quite difficult to do before the advent of fractal capacitors. So I thought I would share all of that with you. I hope you enjoyed the video. I hope it sparks your imagination. Thank you very much for watching, and please do remember to like and subscribe.